Right, so physical agents to radiation and the thermal environment. So I'm making a start, right? So physical agents, we have to look at some radiation physics. The main concept here in the lesson today anyway would be different types of non-ionizing radiation. The effects, not too much measurement today as yet. Measurement is more or less on next week's session. Then you have ionizing radiation, the effects and measurement. So actually today's class talks about what they are. To be honest with you, these first classes, just like noise and vibration, tend to have some physics in it. And you know, NEBOSH is not too big on that with frequency and amplitude and wavelengths and stuff, right? But we have to get those things done. It's just that those things are not very big exam questions in a safety course anyway. The bigger questions are normally the effects and measurements, and perhaps in about 2 classes, while counting this one, so next week and the other week, we can get into some serious past papers. They do have a lot of past papers on radiation, lasers and welding and microwaves and UV rays, where you have people taking a tan in salons and stuff, right? But before we get there, we have to kind of cover the academics behind it, right? So I would not stop till I think there is something worthy of explanation anyway, right? So types of radiation, I could probably summarize, just to be honest with you. I mean, you basically want to know that what we saw on this slide before was that you had 2 types of radiation. You have ionizing and you have non-ionizing radiation. Ionizing radiation having the ability to ionize matter. I would explain that. The slides, in fact, explain it on its own. A non-ionizing radiation capable of producing thermal and photochemical effects, right? This slide does the explanation inside of it anyway. If I pause now, I would be robbing myself of some time, right? So I'll keep moving on. So types of non-ionizing radiation, again, not all is mentioned here, but you have things like in the form of electromagnetic rays, electromagnetic radiation, EMR, they travel through space, have a constant velocity of the speed of light, which is 3 by 10 to the power of 8. None of that is, you know, worthy of a NEBOSH safety question anyway. This form of radiation is mainly characterized by wavelength, which varies over a range known as the electromagnetic spectrum. The wavelength is inversely proportional to the frequency, right? So they mentioned that the non-ionizing radiation typically on the spectrum, and what you see on the spectrum is that some of the units would be in gigahertz, well, gigahertz to hertz, and some of them will be in nanometers. That's just how the spectrum is designed to look. And when you look at it, you see it here, the electromagnetic spectrum. And I guess if you look at it, you'll be able to figure out that on this side here, from ultraviolet, way down to the end here, what you have here is, this is what we call non-ionizing radiation. All of these here, non-ionizing radiation, right? So simply put though, I mean, a question can be, which I don't think it would be at this diploma level, maybe more at this certificate level, to name some non-ionizing radiation. You see them here, non-ionizing sources of radiation, lasers, welding, microwaves, the mobile phone, power lines, etc. Just in case you wanted to get that a bit. And then where this arrow starts from here, this is the ionizing radiation. And these are, you know, the more harmful form of radiation. This is the alpha, beta, gamma, X-rays, neutron radiation, and that's on this slide too. So if I just leave it there, you'll be able to pick it up, right? So what you should be able to tell though, and this spectrum doesn't do that too much, is that as you go along the spectrum, like the intensity increases then, right? So as you go this way, which is not completed here, the intensity of the radiation increases. And likewise, I'm trying to see this one here. likewise, from this side, from domestic appliances, mobile phones, microwave ovens, TVs, to welding, to lasers. As you go this way, the intensity increases as well. Not that you have to know any of those, but that's a way of reading the spectrum. The spectrum normally gives you an idea of like which one is more harmful than the other one. If you take a look at it here, you'll see low, right? Low ELF, and on this side here, extra high, right? EHF anyway. So it gives the idea that the intensity of the radiation is actually increasing along the spectrum. And again, none of that is ready for a safety question. That's more physics anyway, if you wanted to interpret the spectrum, right? So radiation physics, I could read one of this. The energy produced by the electromagnetic radiation is proportional to its frequency. Radio and microwaves has relatively low frequencies, and as you go down, like lasers and stuff, would have a relatively higher frequency, right? And again, not to confuse it though, but once you cut off right here, from right here is the ionizing radiation, and from here, all of these are pretty bad. All of these then, not that microwaves are not bad, and the radiation from your cell phone isn't bad, but as you get into the ionizing radiation, it has more of an effect on tissues then in the human body, right? Think of it as X-rays and gamma rays and neutron radiation and stuff, right? Quite a lot of those are responsible for, or could be, attributed to like cancer-causing agents as well, right? On this side, though, I mean, we have been listening to radios basically all our life. We have been using our phones, not all of our life. I mean, most of us are, sort of pre, the millennium age anyway, right? So I don't think we grew up with cell phones, but we have been using them, and they have not really been any mass, cause of cancer per se then, right? But these do create some form of radiation. It's just that it might not be, as dangerous as the ionizing types of radiation. So non-ionizing radiation is radiant energy which does not have sufficient energy to cause ionization in matter. I'd explain that again. I said it's actually done on the slides, so I'll leave it for those slides. It consists only of electromagnetic radiation, EMR, from wavelengths above about 10 to the minus 7 meters, right? And this piece of maths here, it's the same thing as this. I don't know if you remember any of your maths. Approximately 100 nanometers is the same as 10 to the power of 2 by 10 to the power of minus 9. I mean, this is not for you all, but if you remember your maths a little bit, whenever you see this, if this was 10 to the power of 2 and this is 10 to the power of minus 9, what you had to do with these two is minus them. So 2 minus 9 will give you the same minus 7 you're seeing up here, right? Just to explain those funny looking things, but none of those things are your exam anyway, right? So some types again of non-ionizing radiation, original sources, where you saw some on the spectrum, we have ultraviolet, visible, and infrared. And really for your exam, they normally like to bring one of these. I mean, ultraviolet is highly examined. I'm not quite sure about infrared and visible light. I think I may have seen a visible light question already, but ultraviolet is very popular. And when we get into this, which would not be today, today's still introductions anyway to this thing, you will have to get like what are the causes, what are the effects, and what are the controls. And that's basically the idea behind the whole radiation topic. Whatever they give you, if it's ultraviolet, even if it's X-rays or gamma rays, is basically what it is, what is the effects, what are the symptoms on the person, and perhaps what are the controls. So ultraviolet there, naturally occurring in sunlight, emitted from sun lamps, discharge lamps, arc welding processes. And like I said, there's a lot of questions on ultraviolet light, all right? Especially with where tanning saloons are concerned, right? We may have them in Trinidad, but maybe very big, I guess, in Europe anyway, and in the US. Visible light, naturally occurring in sunlight, emitted from sun lamps, discharge lamps, filament lamps, welding processes, etc. Infrared, naturally occurring in sunlight, emitted from sun lamps, welding processes, emitted from sources of high heat energy, furnaces, ovens, heat lamps, etc. Right? And again, not to boil everything down at the very first class, but when you start looking at this, you notice that all the symptoms are kind of the same. All the effects then is that it either affect the skin or the eyes. So it is that they kind of learn some of those. And actually all the controls are all the same as well too. We may have mentioned some of those controls before. All the controls are kind of like keeping your distance, cutting on exposure time, shielding. I mean, all of them are kind of similar based on what you're looking at. And that's why I said I wanted to tackle these easier lessons after we had completed the harder ones anyway, right? In addition to optical radiation, which normally radiates in a spherical mode, so I can leave this. This sounds a bit like physics, right? I can read out the rest if you want, right? Just maybe this one. These wavelengths of energy can also be produced in a highly coherent form, producing collimated monochromatic beams of energy known as lasers. Their relatively high energy and behavior makes them potentially hazardous. So yes, if you remember the spectrum, lasers is classed as a non-ionizing radiation. So these slides here are just introducing then the different types of non-ionizing radiation. You see lasers on this side, and sorry, my mistake there. Lasers are again highly examined. You would be surprised to see those of us who have not looked at a lot of past papers, how would they bring a laser question? The laser questions, they are not really like space age, you know, like with laser guns and stuff like that. There's not that kind of laser question you're going to get. The lasers here, like everyday lasers, lasers like you may find in the checkout counter at the nearest grocery. There was actually one that was very troubling for some students, troubling in terms of the control because they had asked the question on lasers in a disco, right? But what they call disco across there. I don't know if we say disco in Trinidad still, but I guess a dance hall, right? Like the lasers, you know, when you have parties, you see these lasers, the laser light comes in, and like how do you control that on the effects to the patrons? And that was such a troubling question because it didn't give you the option to say turn off the lasers because it was a disco hall, and that's what people go there for. They go there, you know, I guess for that sort of ambience then, right? So you could not have turned off those lasers and whatever have you. So that's what you would see. This piece, in case this piece frightened me a bit, the collimated monochromatic beams, all that is and I suppose I'll get to that when I get to lasers, which would not be fully today, but all that is, right? That word means that the beam of lights are traveling parallel, but it's actually concentrated. So the beams, the word collimated means it's parallel beams of light, right? Parallel beams of light. And that's actually what's going to kind of give you that laser light, and because the beams has been concentrated, right? So the beams has been concentrated, and that's what gives you that focus of the laser anyway. Collimated though means that they are parallel and they actually do not ever converge then. I mean, parallel lines do not converge anyway, right? Nonetheless, I mean, all of those funny looking things are still physics, right? But just to kind of clear up things we have on this slide, let me get that eraser, right? But nothing really there, you know, I think that it's too worthy of questions. It's good stuff to know that you understand it anyway, but nothing too worthy there anyway. For exam, when I say worthy of exams anyway, right? I think we still need to know for now. I mean, the main thing for me is to know that laser is a type of non-ionizing radiation. So is ultraviolet light and sunlight and radio waves and microwaves, etc. Right? All right, moving on. That's a little too much explanation. So non-ionizing radiation, again, original sources. So we are going to still the same heading. There's different types. You have microwaves used in communication systems, alarm systems, cooking, of course, diathermy, and this is actually surgery, for want of a better word anyway, right? Diathermy is where they would use, like, again, you could probably think of it as heat, I want to say lasers to give you the idea, but it's not really lasers. It's like you would use heat in surgery, maybe to like disrupt um, certain growth there, like a tumor, right? So if you see diathermy, there's the use of heat in the body itself to maybe like disrupt a tumor. It might not be cancerous because not all tumors are cancerous. Some could be what you call benign anyway, right? Meaning that it's not cancerous. Nonetheless, that's a good set of stuff to learn there for microwaves. Not that, you know, I mean, at the diploma level, I don't see they giving you 4 marks for knowing um, 4 sources of microwaves. I consider that more for the certificate level students. At your level, you may be lucky just to get 2 marks, right? 3 for the most, right? 4 marks to waste on an origin question is not likely to be a diploma question anyway, right? Anyway, radio waves naturally occurring. So we talk about this. I don't know if this could be mentioned now, but there is actually naturally occurring radiation on the Earth. There is a famous one. I would probably mention it now, but please note that's not today's lesson. There's naturally occurring radio waves due to like the Earth magnetic fields, and they actually naturally occurring radiation. Anybody know of one? There was a heavily tested one at the certificate level, and it's actually famous at this level too. Another naturally occurring form of radiation. It starts with an R, and it has a very short name. Anybody? Well, that one is actually called radon.
Radon.
Right, radon. And there's a lot of questions at diploma level. I don't want to go into that now because there are whole questions on radon anyway, right? So if you didn't know about that, there are naturally occurring radiation on the Earth. It's a nice theory if you like, and I often like to give you all the the weird side of topics to kind of make it interesting nonetheless. I mean, there are a lot of theories on how the radiation came here. Some people said it came with a comet smashed into the earth and it resulted in radiation. Some people said that there have been nuclear explosions in time gone by, right? And there are radiation left over from that anyway, right? I don't know if anybody, I often look at some of the weather shows on TV anyway. I had mentioned there's actually one called, if you haven't seen this one is worthy of finding some old episodes. I mean, old being last year because since the lockdown, they haven't been able to do any more episodes of it. If you have seen, it's on the History Channel. You can find it on YouTube, by the way. If you just want to see one little snippet of it, it's called, I think it's called The Secrets of Skywalker Ranch or something with Skywalker Ranch in it. And if you haven't taken a look at it, please do so because it's just ranch where weird stuff happened in the US, but weird enough to know that when they actually brought in instruments, they got high levels of radiation on the ranch, right? Higher than probably what you'd find like in a nuclear plant, but there is no evidence of history of nuclear radiation there. One of the episodes of this is so interesting because they actually pinpointed the source of some sort of source of where it was coming from. They use, I don't know what instruments they use, but they kind of got all these rays to kind of converge to see where it's coming from. And the strangest thing ever, now again, this is the History Channel, right? This is not something that's made up, right? It was actually coming from outer space. The source of it was a signal coming from outer space, right? And I guess that's how wrong this series came to an end because of the lockdown anyway. So nonetheless, the story about that is that yes, there is naturally occurring radiation. However, it came here, the point is it is on the Earth anyway, right? So we have radio waves, satellite communication, radio waves transmission, medical application, for example, MRI. All of those would be, you know, different uses of radio waves anyway. Right, so this is the piece I kind of getting into now when they spoke about the difference between ionization and non-ionization. If I see the time going and we are reaching, I'll probably just do the explanation for you, but I want to stick to the slides a bit. So ionization of matter occurs when orbiting electrons are dislodged from their atoms. This results in the formation of a positively charged particle called an ion and an electron negatively charged, normally referred to as an ion pair. The electrons are very active and will eventually react by attraction or collision with another particle to produce a negatively charged ion, or neutralizes a positive ion to give a neutral atom or molecule. Again, if you have not done chemistry, you'll find it very confusing, but I intend to do the explanation on the diagram, right? Structure of matter made up of molecules, which are in turn made up of elements or atoms. The simplified Bohr model of an atom is as follows. So if you don't know this, I'm probably gonna have to put my marker on this one, right? This is the basic idea of an atom. And if you don't know what an atom is, this is the smallest part of a molecule, you know, like an element that cannot be subdivided. Now, even though they say that the atom has three distinct parts. You have the center, but it's called the nucleus, right? You have the outside here, and these are called, well, these are called shells, right? Some people call them orbits or orbital shells, and in those shells, you normally find the electrons on the shell, right? So you do have, you'll see this, hopefully this don't confuse you all, and it is not really meant to be, too much of physics. So you do have about 3 shells out there. This is how an atom is created. You have the first shell is actually called a K shell. The other shell is called the L shell. And the other shell is called the M shell, K, L, and M. The inside of the atom is called the nucleus. So let's put an N here. And in the nucleus, what you find here, and I just would draw that as a separate thing. Let me show the divide this here, right? So in the nucleus, you're gonna find protons and you're gonna find neutrons, right? In the shells, or these things we call KLM, we find electrons there. So these things you see out here are electrons, and inside here you see they have red and blue. Well, one will be representing the protons, the other one will be representing the neutrons, right? But what you're looking at here, if you can look at this carefully, what you're looking at here is a stable atom, right? Actually, the word atom has a lot of history behind it, which I wouldn't go into now, right? The word atom has a bunch of history behind it as well, right? But what you're looking at is an atom. Now, why is it stable? It's stable because you have the same amount of everything, right? Inside of it, supposed to have protons, out here supposed to have electrons. And if you look at that, you see three blue, that's your protons. You see 3 darker circles, that's your electrons, and then you see 3 reddish circles, that'll be your neutrons. But it's 3 of everything. And if it's 3 of everything, it means it's exactly balanced. Why is it balanced? Because you have 3 protons, and really it's because you have 3 electrons. And why this is balanced is because electrons are negatively charged, protons are positively charged, and when you put the 3 protons with the 3 neutrons, they'll balance off to give you what is called a stable atom. So the overall charge is 0. Now, this is the type of radiation that's called non-ionizing. The energy given out here, right? There's energy given out from this, right? The energy given out from this then is what they call non-ionizing, right? Because the atoms are stable. So this is like your microwaves. This is like the UV radiation, right? This is non-ionizing. This is microwaves. This is the UV, etc., right? But when they start to refer to ionizing, I'll just do the explanation here. In ionizing, something happens, right? I guess the scientists are not quite sure, but they say there's like an input of energy, and what would happen, it would cause something to make this stable atom unstable. And when that happens, what you have there, like for example, if we lose an electron, let's say we lose this electron, if we lose the electron, meaning we now have 2 electrons, we are going to end up with an overall positive atom. This wouldn't be 0 anymore. This will now be +1. So then the atom will have a charge, and this here is now what is called an ion. This though is actually referred to as a positive ion. Ion there is short for ionization, and then this now will be a form of radiation. Like this will now be like alpha radiation. Alpha radiation is a positively charged sort of radiation anyway, right? So once you upset the flow between the number of protons and the number of electrons, you have an ion being formed, If it was the other way around, and let's say maybe you would have lost a proton, you end up with a negative ion, let's say -1, and then that's called again, that's a negatively charged ion. And then the energy given out there is what we call ionization energy. So what is ionization energy? It's the energy needed to bring the atom then into like an unstable state. The unstable state can happen positively or negatively. However it happens, and what you end up there with is an ion resulting in ionizing radiation. Right? So if you read over that slide before, you'll see it makes a lot of sense now, right? Again, I would choose to leave that there. I would read it over once because, I mean, that's just an explanation so you would know what is ionizing radiation. And you could probably figure out that it is, because of all of that instability to the atom, it is going to be a little bit more harmful than the other forms of radiation. I'm still trying to get my cursor to change back to what it was. Right. And it still didn't change back there. Right, so I wouldn't be able to move forward or backward with that until it changes. The pencil is still on the thing and I'm clicking the, not too sure what that hand is doing there. I definitely didn't click that. All right, I think it went, so I'm gonna keep going, right? So electrons have a negative charge, protons have an equal and opposite positive charge, neutrons have no charge, right? Same number of electrons and proton in a neutral atom. A negative charged electron attracted to a positively charged nucleus. And a neutral atom which loses an electron becomes a positive ion because you lose a negative. So you mean with a positive then, right? A neutral atom which gains an electron means you take on another negative something. Negative electron means you become overall negatively charged ion. Nonetheless, that's the whole idea of ionization. You can read through this if you want. I could probably read one because it just goes through different, laws. If you look at this one here, we have, I'm seeing 3 electrons. I'm seeing 3 protons, 3, okay, so 3 positive protons and 3 electrons means a neutral atom. So this one is neutral. If you try to figure out this one, we are seeing 1, 2, 3, 4. And these are the shells I was talking about, the K shell and the L shell and the M shell. Those orbiting rings are called shells. I am seeing 1, 2, 3, 4. So what this would be, what this is overall, negative or positive? Anyone? This is a simple one. Overall, this would have a negative charge, right? Adding an electron leaves us with a net negatively charged ion, right? So that's the idea that when the atom becomes unstable, you end up with an ion and the energy given out, ionizing radiation, right? So this is one of the first types of ionizing radiation. It's called alpha radiation. Again, there's a lot of questions on this, so I want to go to this slide. What you're seeing here, a lot of people mix this one up, though. A lot of people mix this one up. And what I mean mix it up, they feel because it's the first one. Remember, in the list of ionizing, you have alpha, beta, gamma, X-rays, neutron radiation, right? So a lot of people feel because this is the first one, it's not harmful, especially when what this slide is showing is that alpha radiation could be stopped by a layer of toilet paper. Alpha radiation could be stopped by the surface of your skin. So the misconception here is that people feel that because it could be stopped by a sheet of paper or the surface of your skin, it's not harmful. Well, that's not true because this belongs to the category that we just saw. This belongs to the category of ionizing radiation, meaning it's more dangerous than a laser. The only thing is that out of the 5 of them in ionizing, it could be stopped by, like external paper, but that doesn't mean it's not harmful. The trick at alpha radiation, and this comes, for example, I was telling you all, is that once inside the body, it creates havoc then, right? But it could be stopped with a sheet of paper. That doesn't mean it's not as bad or worse than or 100 times bad than a laser anyway, right? So the process of ionization, which we just explained, the process of ionization was the gaining and the losing of electrons, require an input of energy. Now, where the energy comes from, scientists are not sure. They say it just happens. The formation of an ion pair causes the radiation to lose energy to the matter involved in the collision. And that is where we get the waste energy, then is where we get the ionizing radiation from. Ionizing radiation generally is categorized as alpha, beta, gamma, X-rays. This is X-rays if you want to just slip that one there, and neutron radiation. But like I said, it seemed to be that NEBOSH loves alpha. X-rays have come before, not a lot on beta. In fact, probably none on beta. Probably none on neutron radiation. But there's a misconception that people realize, or they feel because alpha is first here, it means it's not bad, especially when it could be stopped by paper. But it is that harmful form of energy known as ionization, meaning that it is worse than the worst on the other side. And the worst on the other side of non-ionizing was lasers, but this is way worse than that. It's just that it could be stopped by paper. That doesn't mean it wouldn't cause total devastation if it gets inside of the body. Right? So alpha radiation, alpha particles, consists of 2 neutrons and 2 protons. It results from nuclear decay. It is relatively heavy and doubly charged. Alpha radiation has a very short range. It is stopped by a few centimeters of air, the thickness of a sheet of paper, the outer layer of the skin. It does not present a significant hazard outside the body. It can cause the intense ionization, biological damage internally, where it may make immediate contact with tissues, examples, the lungs, right? So we'll have to, I guess, wait till we get into our paper to see all the trick with alpha radiation, but some things is right on this slide. If I could read between the lines, you have, they say it consists of 2 neutrons and 2 protons. I had mentioned this before. Neutrons have no charge. If it have 2 neutrons and 2 protons, it means it's positively charged. Alpha radiation is a positively charged form of radiation, right? Could be stopped by air, but once inside the body, it will do what it will do, which is, cause damage to tissues, destroy those tissues, burn those tissues, resulting in things, like, of course, the worst case, cancers and growths, and coming out of that, even death, right? Beta radiation, the beta particle has mass and a charge equal in magnitude to an electron, meaning that it's negatively charged. In case you want to read between the line, if it has a charge equal to the size of an electron, it means it's negatively charged. Its penetrating range in tissues depend upon its energy. Low energy beta radiation would not penetrate the outer layer of the skin. High energy beta can penetrate soft tissues to a depth of 1.5 centimeters. Gamma rays and X-rays, I'll read it from this slide, but in a way, these are 2 separate things, and these have been tested separately as well, right? So don't think of it as, it's gamma or X-rays, is exactly gamma and X-rays, right? I think a question I saw that was troubling, troubling when we did it in class, and the response from the students, they had asked students, what is X-rays? They define the term X-rays, right? So I guess when we get to that, you can probably review that question anyway, right? So gamma rays and X-rays are both forms of energy propagated in the form of electromagnetic waves. That's what the whole class is about anyway. All forms of radiation typically is in the form of electromagnetic waves, right? Gamma radiation is emitted continuously by radioactive decay. X-rays are generated in electrical equipment when a metal target is bombarded with a high energy stream of electrons. So this is kind of like what they were asking for. Because of the way in which these rays are produced, X-rays are only present whilst the machine is switched on. Gamma rays continues to be emitted until the source has been depleted, right? For example, like in power plants, etc., right? So a nice little thing here was how would X-rays, or how X-rays produce. Again, we could look at the participles in due course to sort out the differences in that anyway. The penetrating power of electromagnetic radiation depends upon its energy, the properties of matter it interacts with. X-rays can pass through human tissue. Ionizing radiation has the ability to react with fog, photographic film, hence its use in medical application, non-destructive testing of wells, etc. Both X-rays and gamma rays can be stopped by using lead shielding. Gamma sources are also used in research and the sterilization of medical products, right? So a typical X-ray here of Homer Simpson's brain. Again, like I said, normally when I do these things, sometimes to make it interesting so that you go and you learn it. It'd be interesting if you just research the first person that discovered X-rays, right? And it was actually a lady, by the way, and when she first saw it, I think they discovered it by mistake, right? So I wouldn't call her name, right? It starts with an M, right? So you can go and research that a bit. Anyway, I may sell it out at the end of the class, right? But they discovered this, I said they because it was actually her and her husband. And her husband is a little bit famous as well, right? In terms of scientists. And when they discovered it though, it was by mistake. They had left the machine on anyway. And it was the first time that human beings then could have seen their skeleton, right? It was the first time that they could have seen their skeleton. And she was actually scared. It actually haunted her. For those of us who know the story, it haunted her for the rest of her life. A picture of her skeleton, right? It haunted her for the rest of her life because I suppose they didn't think of it having medical applications back then. But she said her exact words were, she saw her own death, right? When she took the picture there, and she said she saw her own death because she could have seen her skeleton, right? And it haunted her for the rest of her life. So again, that's interesting. If you just do the little thing on research it a bit and see who came up with, who the first discovered X-rays, and they didn't see quite the use of it back then anyway, right? Today is of course normal to get an X-ray done, right? Broken or fractured bone or whatever have an X-ray is one of the first things that they'll have taken in the medical industry, right? So neutron radiation is looking at the time, neutron radiation. So neutrons are emitted during nuclear processes such as nuclear fission. And again, those are some physics terms there. You have two types of, neutron radiation. You have fission and fusion. They are uncharged, therefore they are unaffected by electric fields around the atom and consequently have greater penetrating potential. But again, you should know in the sequence of them, you had alpha, beta, gamma, X-rays, neutron being the worst one anyway. Neutron produce ionization directly and can cause significant harm as they pass through the body. Neutron sources are used in power generation, medical research and treatment, radioactive sources with a short half-life. Again, that's a physics term there. You don't need to know all of that. But if you do want to, you can check it out a bit. Half-life is just the number of years it will take for half of the substance to break down, right? And so for some radiation sources, it is actually hundreds of years, right? For half of it to break down anyway, which is why I said that some scientists have speculated that there would have been neutron bombs and whatever have you on the earth before, and it would have taken thousands of years for it to break down, which is why you can still get high concentrations, like in that place I told you in the US, high concentrations, more than a nuclear power plant. But there is no known history of nuclear power plants on this site anyway, right? So they take thousands of years to break down anyway. Radiation organization, just about 5 to 11. So you have about two main ones here. I don't think I want to read all of them. I suppose you could just shout out the name. I have seen questions like this before, and they have asked like, what would be external bodies then that would be interested in maybe knowing that an employer has, you know, radiation sources on their work, maybe X-ray machines, maybe um, the ones they use for non-destructive testing. So that's how these tend to come out of the external sources. So they have more than three though, but I suppose I don't see that for being more than 3 marks. I can see like a 2-mark question. So you have the International Commission for Radiological Protection, and that's actually really what it says is an international commission, and the one unique to the UK is known as the Health Protection Agency, right? So this is like one over Europe, if you want to think of it like that. The International Commission for Radiological Protection, and they have been around for a long time. You can just see that's in 1928, and they went through some name changes and stuff, right? They work with things like international collaboration for standards, units, and research, and we will learn this in the upcoming classes. There is actually set units for radiation, just like everything else. You know, noise have the units, decibels, vibration meters per second squared. There are a couple of units for radiation, but the one mentioned in the law, you'll see that in the weeks coming up, they have particular units, and then you have particular concentrations, just like noise is 80 decibels and hand arm vibration is 2.5 meters per second squared. They do have limits for radiation set for employers that deal with radiation on a regular basis, like those non-destructive testing places, medical research labs and stuff. So those that have been set up by the ICRP, and then of course you have locally, when I say locally, I mean local to the UK, you have their own UK bodies like the Health Protection Agency, a UK government funded body, right, created under the Radiation Protection Act, and they work together with the rest of them, you know, to set standards and stuff, to do research, right, to improve knowledge, protect individuals, provide robust advice and guidance. And that's actually what comes in a lot of the laws. That's what would have formed into a lot of the laws, because if you look at the years, like I said, 1928, you didn't have no health and safety law at that time. And even 1970 here, the very first law they had in the UK was the HSW Act, 1974. Today, the radiation laws, I think, carries the year 2005. Some of them could be 1999, right? At least some of the older ones anyway. But still, you would have known that it is the work by these organizations that would have influenced those standards anyway, right? I explained it based on the time. So they say in the board, right? The board of the board of this organization here, the Health Protection Agency, what they do, they work together with the HSE, right? And again, the reason why I say HSE and I say in HSC, because those of us who did Unit A before, you know that the HSC does not exist the way it did before. Now, since 2008, in fact, the HSC was more or less taken into the organization known as the HSE. Nonetheless, though, the whole story here is that the board is going to work with the government agencies in setting standards, right? Whether or not back then, you know, I mean, when they first did it, was called the HSC, but of course, 2020, we now have to refer to this as the HSE, right? So what do? They work together, the board of the Health Protection Agency, they work together with the biggest UK health and safety body, the HSE, right? In coordinating and representing the UK's interests, coordinating national arrangements and standards for things like radioactivity, helping to determine suitable standards and training for officers responsible for radiation safety, right? So that's a lot of good stuff there. Again, if I was to boil it down into a passive question, coming out of that, maybe what would be 2 external agencies responsible or that could be influential in an employer, you know, looking at, you know, I would try to say set their own standard, but again, the standards have been set by the law already, but maybe complying with those standards. What is 2? We actually have 3 on this slide. You can go with the International Commission for Radiological Protection. You can go with the Health Protection Agency, and you can go with the HSE, now called the HSE, right? That happened in, I think, April 2008. The HSC was taken into the HSE. And when I mean into, if you don't know what that means, the HSC is a real building in London, right? It's a real glass building. So taken in meant that they have like a department then within the HSE building that is in London, right? So they still function, but there is no separate organization called the HSC anymore. They function within the HSE, right? So maybe I should bring this one to an end here and leave this one here for next week, right? So I could just read out this one, right? The Health Protection Agency acts in consultation with the HSC, which happened back then. HSC are required to consult the Health Protection Act with respect to regulations. This WRT means with respect to regulations, approved codes of practices, etc. And you would expect that if they are going to come up with a standard, they'll want to see what the law have in it, what the approved codes of practices have in it anyway. The board, which is the board of the Health Protection Agency, has responsibility for specifying the emergency reference levels, right? And we learned that, I can tell you now, I mean, but you learn that, you know, as the lesson go along anyway, right? Following an incident at a nuclear installation, the emergency reference levels refer to the level of radiation dose received by the public, below which countermeasures are unlikely to be justified, right? And it is a figure. I can probably show the figure now and we'll pick it up next week, right? Because the class is about to be finished. So the figure is at least 6 millisieverts, right, from members of the public. And then there are certain situations that the limit will actually come to 1, in fact, 1 millisievert anyway. So all of those specific requirements will have to come to in the upcoming classes. But I suppose just to keep it interesting, as we mentioned in standards, I'll call a standard, a real standard is actually 1 millisievert, and then there's also 6 millisieverts if you are actually working with radiation as part of your normal work, right? And we'll clear that up in the weeks coming up anyway. So let me see if you have any questions there. If anybody have any questions there, if not, we will close off this session, right? Again, some nice little concepts today. Again, to me, nothing too difficult. And maybe nothing too much for exams either, right? Simple questions I find, maybe 2-mark questions, 4-mark questions. What is X-rays is a nice one. I guess from today's class, you must be able to distinguish what is a ionizing source of radiation to what is a non-ionizing source. We went through what is ionization. Quite a lot of physics, not too much for safety. The real classes will get started, or the real exam, they will get started when we start looking at effects and control really for radiation. But again, you would have probably picked up from what I'm trying to do. I did mention that I wanted to do some of these easier topics last, and that's exactly what's happening. This is gonna go until the end of radiation. And then the other one is even, I find, more straightforward. Is actually one on stress and mental health and violence and work and bullying and stuff. Really, you know, easy going mentally anyway. And I think once you get it done, you should be able to do the exam, right? I'm going to stop the recording. Let me see if